Okay, so let's start again after the break, and I'll make sure we finish at 10 to before the end of the session. With the k-nearest neighbor algorithm, we finished the part that we're doing on supervised learning. And what I'm going to be doing at just in this lecture is looking at an alternative approach of unsupervised learning, where you don't have the labels from your classes. Now, this may not seem to be particularly useful if you think, well, usually you want to know an answer from something, but sometimes it is useful for us to do analysis on data, even if we don't have labels that go along with it. Sometimes, I've given an example before, for example, of where you might want to work for a supermarket. Yeah, come in. You might be working for a supermarket and you might want to cluster your customers into different market segments that you can target in different ways. There might be also, you might have a large amount of data that's going to tell you things that you could use for making later stages simpler. And we'll come across later an example of the so-called Kahun-Loew transform, or principal component analysis, that can be used to reduce the dimensionality of data. So that's an unsupervised learning type method. But for this one, what I'm going to be focusing on is the use of clustering algorithms. So sometimes we don't know the labels. The labels are expensive. We often have to get a person to assign those. But there may be some useful structure that we know about. So if we look at this visual example here, we can see that there is a sort of, there looks like there's a sort of lump of, maybe one or two lumps here of data. There's maybe something here, maybe a sort of banana-shaped lump over here. And these are things that it might be useful for us to be able to put those into particular so-called clusters. And these are usually based on the idea that points are clustered together if there are similar things in high density areas. So where you have very similar data points, they'll actually be physically closer to each other in the measurements that we make. Yes? Yeah.
You mentioned the banana shape of a lump.
This one here, yeah, so maybe this shape may be one cluster around here.
How do you know it's not like two different, like one horizontal and one like, how do you know it's like the banana?
Yeah, that's a very interesting question. We don't know. So when you're dealing with unsupervised clustering, there are a lot of choices that you can make that may be on the basis of guesswork or experience, but you can't guarantee that you're going to get the right answer from something. So one of the questions that often comes up with clustering is, how many clusters should you expect? Or is there a sort of criterion that we can use? And we'll see at the end of the lecture that there are sort of tree-like ways of building a tree of clusters which could cluster, single points in one cluster, all the way up to all the data points in a huge, massive cluster. And so sometimes there are some choices to make, and we might need to look at, is there a natural break point in that tells us where some natural clusters are? If you can plot things in 2 dimensions, sometimes you can naturally visualize these things. Otherwise, I've seen, for example, when I was doing some work with the Research Council, they were trying to cluster different research topics together. And so they asked people questions, you look at the similarity of the questions, and then you try to say, oh, well, maybe there are these 6 different research topics and we need an expert group in each of those areas, but that research topic is very different to this one. So I work in sound recognition. It's a bit like image recognition, but it's completely different to photonics. And so these are the sorts of things that might come up that might help you cluster topics. So there is the sense that we need similarity measures to use to say how similar are 2 points. So it's a bit like the k-nearest neighbor algorithm that we talked about before. We need to measure the similarity of points to find its neighbors. We're doing that almost completely based on neighbours here. And there are choices that we can make about which similarity measures to use. Often one that we start with is the so-called Euclidean norm. That's the normal square mean distance that we would use. And these could be clustering either point to point. So we could say we keep clusters together if the next point to it is very close to it. Or another one is that we have a single mean for the cluster and we look at the points that are close to that mean. And we'll see in one of the algorithms that we'll introduce in a moment, the k-means algorithm, that it uses this idea that each cluster has a particular mean, and we look at how far those things are away. And so we need to have some sort of measure or criterion, a rule that tells us how to cluster things. So if you did it by eye, you might just draw lines around things and say that's one cluster, there's another cluster. But if we're going to use it using an algorithm, we need to have a criterion or a rule that we're going to use. And usually the rule is related to some sort of similarity between data points. And so what we're going to start with is a practical example of this, the k-means clustering algorithm. And for this, it's a bit like the Gaussian classes that we had before. There's an idea of a mean, and then all of our data points, we can measure how far they are away from that mean. Now here, for the k-means algorithm, we can use a very simple model. We can see it's a bit like in the Gaussian normal model, we had a sigma to the -1 in here and an exponent for something. Here we're just going to use the squared distance, x minus mu transpose x minus mu. All that is x minus mu norm squared, the two norm distance. We don't even bother to take the square root because we're just comparing them to each other. So the square root would be an extra operation that we don't need. And so this is the distance of every point to the mean. That says how close is this point to that mean. And the clustering criterion is the sum of all of the points and the distance of all of those points to the mean that they're assigned to. So if we had a cluster mean here, mu1, and a cluster mean here, mu2, we could have data points x1, x2, x3 that were assigned to mu1, and we could have x4 and x5 that were assigned to mu2. So we would measure the distance of this point to that mean, this point to that mean, this point to that mean, and then this point to that mean, and this point to that mean. And this total sum will give us a measure of how good or bad this clustering is. And you can probably see from the way I've drawn this one, it's a little bit imbalanced. You might think, well, x2 looks, maybe it's closer to x4 or something. And this is actually the key to how the k-means algorithm works. You look at all the data points and you say, is it assigned to the class with the nearest mean? If yes, then we're fine. If it isn't, actually, if we move it to a different class, then we'll reduce this clustering criterion cost. So think of this as a badness of the clustering, and you want to get this badness as low as possible. Now, the other thing that allows the badness to get less is if you move the mean of the cluster to the mean of the data points that it's in there. It may not be so obvious from here, but actually if we move this mu towards x2 a bit, move it to here, we can see the distance to x2 has got smaller. The distance to x1 and x3 has also got a bit smaller. So that's also reduced the sort of badness or the cost. So there are two things that we do, and normally we iterate between these two things. There's a slightly cleverer way of doing it that we'll see in the tutorial. And this iterative algorithm says, suppose that we transfer a point. Let's say we're going to transfer x2. And instead of assigning it to that class, we now assign it to that class. What change is going to happen? So if we've got lots of classes, suppose we've got another class here with some more means, these won't be affected by this change. Only these two classes will be affected, these two clusters. But the effect is slightly more complicated than you might think, because when we move the point into another cluster, the mean also changes. So we have to update the mean, then we have to update all the data points. And we end up with this slightly awkward looking criterion that's got an NR over NR plus 1 because of the sort of, the fact that we've moved the data points means that the means have moved inside here. So I'm not going to derive this here because this is an exercise in one of the tutorial sheets. So you'll be able to derive this formula to see how this comes out. But that is the one that you should get, and you'll find out how you do that from, if you move the data point, the mean will change, and then also the scores to all the data points that you've moved will change. So you can then use this criterion and go through from every data point. You can say, right, I'm currently in one class. What would happen if I moved to all of the other classes? So suppose here we've got 4 clusters. If I know I'm in this cluster, I take this point and I test what would happen if I moved it into this cluster, or this cluster. And you do that for every data point. And then if you find that moving into another cluster will reduce that clustering criterion, you move it. And then you take the next data point and do the same again. If I move this data point, will it reduce the clustering criterion? You have to recalculate cluster means every time. So every time you move a data point, both cluster means will move. So one of the interesting things here is that we've got a global criterion, we've got a global cost, the badness of the whole clustering thing, but at every point, the decision that we need to make is only determined on what happens with these two data points, these two clusters and that data point. So actually it's something where even though we've got a global criterion, the rule that we use is just based on local decisions. And that's a general property that comes up in other sort of things like spin glass models and energy things and so on. The total energy of a system can often be made up of the energy of all the different parts added up. And if you want to flip something, you can actually make a local decision about whether or not to flip it just based on some local things. You don't have to look at the whole system to make that decision. So we'll show a graphical example in a moment, but here's the steps of the algorithm. So first of all, we choose an arbitrary partition of the data set. So initially, we'll arbitrarily assign some data points to one and some to another. There are some slightly nicer ways of doing it. So if you're being slightly clever, you can find a principal component direction and put one class over one end and one at the other end, and that gives you a good starting point. Once you've done that, then you calculate the mean vectors. So what are the current cluster means? And then select a point and check that criterion that we had on the previous slide. And if you need to reassign it to the closest set, and then carry on. And if you have a pass through all of the data set and you don't do any reassignments, then you stop. But if you did any reassignments on the previous stage, in theory, you should carry on one more. Now, an interesting thing about this approach is that because there is an energy function or a total cost function, and the total cost function can't be negative, So let's just go back a couple of slides. This total cost function can't be negative, and every time you do a reassignment, you reduce it. If you're a control theory person, you'll know that this acts like energy, and eventually you're going to reach the bottom. There will be a minimum, so it will stop after a finite number of steps. So the k-means algorithm will eventually stop. You may not necessarily be at the optimal position, but you will stop. And so that's something that, although I'm not going to cover the theory for that, that's quite reassuring that you're not going to keep running the k-nearest neighbor, the k-means algorithm forever. So if you're interested in these type of algorithms, there are people that work on theoretical optimization algorithms, and this is a nice property of being able to make sure you stop. So let's go through a sort of pictorial example to say, here are some data points that we'd want to cluster. And by I, you might say, okay, well, we've got a sort of a cluster over here and a cluster over here. So we'd hope that our algorithm will come up with that type of clustering. So suppose we're going to be completely dumb about the first assignment. We're going to randomly assign all the data points to either one cluster mean or the other. So here we've assigned it to some to black, some to red. Now, actually, because it's random, the cluster means, the mean of the red ones and the mean of the black ones are going to be very similar. There may be a few more red ones over here, so probably we're going to have a red mean a little bit more in that direction and a black mean a little bit more in that direction. And sure enough, that's what we see on the next slide. So here's the red cluster mean, here's the black cluster mean. They're a bit tight, but so actually you could see that a better initialization that we could do if you found a principal component direction and chose to split it halfway along, that might give you a better way of splitting the classes. But now that we've got these cluster mean points, now we can use the rule that we had before and look at each one of these cluster points. So this one here, the red point, if we change it from the red cluster mean to the black cluster mean, will it decrease our cluster cost? So we have to use the formula that we had on the previous slide. The mean will change very slightly, but approximately there's a simpler algorithm called the ISO data algorithm that doesn't actually consider about moving the cluster means. And so actually for that slightly simpler version, which is almost the same as this one, you just draw a line and say, if you're on this side of the line, you assign it to that one. If you're on this side of the line, you assign it to the red one. So that one sort of holds off moving the means until later. It's not quite as good, but it approximately does the same job. So once you've done that, on the next slide, we've now got all the things on this side associated with the black cluster mean and all the things on this side associated with the red cluster mean. Now notice, because I've been using this sort of approximate version of the algorithm, I haven't updated the cluster means as we went. So I now have to do an update for the cluster means to the centroids of those data points, and that's now what we've got. So now the black cluster mean is here and the red cluster mean is here. Now I need to go through all the data points again to see do any of them need to be reassigned. And in this case, I was lucky. In this case, none of them need to be reassigned. But in a real example, it would be very likely that some of these around that boundary, because the cluster means have moved, may end up in a different class, and so we might have to move them. Yeah, question.
Is there a chance that since you start with randomly partition, so because it's randomly, and if the mean of the black and the mean of the red just be at exactly the same position, and the algorithm will run forever since there's no change in it?
Yes, you're right. So the question was, if you randomly assign something so that the cluster means end up at the same point, then you can't distinguish them and you can't differentiate them. So that's a condition that you might need to test for. Another condition you might need to test for is that sometimes different starting conditions are you put your cluster centroids in random places irrelevant of where the data is. Sometimes one of them is near to all of the data and another one is somewhere completely different, or it's near to just one data point, in which case you end up with one cluster that got one data point in it and the other cluster has got all the other ones, and that might not be what you want either. So sometimes, depending on where you start, you end up with slightly different positions for these, and it can get stuck. If you've done any other optimization or machine learning stuff, people talk about a local minimum. So there's the idea that there's this sort of some bowl shapes. A local minimum is up here. The global minimum is where you really want to get to the best answer. But you may not get there. It's like if you want to climb a mountain, I don't know if any of you have done this, you climb one hill, and then you see the other one over there is a bit higher. And you should have started and gone up that one first. So in order to get that one, you have to go down again and then go back up. And so you're stuck, in this case, on a local maximum. And these types of algorithms can suffer from that. So that's the k-means algorithm. There are these two slightly different versions. There's the optimal version and the sort of suboptimal version, but there are a couple of questions in the tutorial sheet to have a go at those. And so really, I think just one more other point that I wanted to cover from these was to finish off by looking at other types of clustering algorithm rather than the k-means. So the k-means is an iterative algorithm where you start by knowing the number of clusters that you have. But it could get stuck in certain areas, and you might have chosen the wrong number of classes. So a different approach that you can take is a so-called hierarchical algorithm, where you gradually build up by either a bottom-up or top-down method. So the bottom-up is called agglomerative, which means pulling things together. And in that case, you start with each of the data points in its own little tiny cluster. And then you look to see, can I join two data points clusters together? And I usually look for the nearest ones to move together. And then I look for the next closest and the next closest and so on. And you find the two most similar clusters each time and merge them. The divisive, you start with everything in one big cluster, and then you look to split that cluster into two, and then split the next clusters into two, and so on. And you need to use some sort of similarity measures for each of these. So nearest neighbor could be a similarity measure that you use. So if you're using a agglomerative, you could say, I've got a cluster so far, let's look at all my clusters, see what's the nearest one that's not in that cluster that I could assign. So you can sort of see where the nearest links are. You can also use this mean cost that we had earlier on. If we just go back a few slides, we had this cost function here. This cost function you can use in an agglomerative clustering method by saying, if I merge these two clusters, how will it change this global error? And I'm going to merge the two clusters that change this global error the least, and like we did with nearest neighbors, it's possible to make that decision just using local information. So I'm not really going to go into the details of that one, but I will show a couple of examples of the differences that it makes. So if we've got these three clusters, for example, the black cluster and the red cluster and the sort of bright green cluster here, if we were looking to merge these based on the nearest neighbor, which is this line, we would look to see what are the neighbors between these two clusters, what's the nearest neighbors between these two clusters, which would be this one and this one, what's the nearest neighbors between these two clusters, which is probably that one and that one, and then we choose the nearest ones of the nearest neighbors and merge those two. So this one tends to give clusters where it's a sort of link-based thing. You've got to find a path between all the data points. An alternative is the mean-based cluster, where you look to see, let's merge the clusters that have the closest mean. So you look at the mean of that one and the mean of that one, and see the mean of that one to the mean of that one, and then the mean of that one to the mean of that one. And you choose the closest of those cluster means, and you merge the ones that have the closest cluster mean. And if you want this to work for the global mean, you need to weight those by the number of data points in the cluster each time. An alternative that you can do is that maybe you want your eventual clusters to be as compact as possible. So what you want is that the merged clusters need to be within a smallest volume. So if we merged this cluster and this cluster, the furthest means would be, the furthest neighbor would be this point to this point. And that would give a cluster that extended quite a long way. On this one, the furthest mean is from this point to this point. And actually, if you measure those two, this one is not quite as far. So it gives you a slightly more compact cluster. So these are different criteria that you can choose. And it's really down to the type of problem that you're trying to solve, which one is going to be most appropriate for what you want. So let's have a look at a sort of visualization of what would happen with an agglomerative clustering method, just so that we can follow through the steps. And again, you'll have a go in one of the tutorial sheets at one of these. So we start in the first step. Each point is in its own separate cluster. So if we've got n data points, if we've got 100 data points, we've got 100 clusters. It's a bit sort of meaningless at that stage, but that's our starting point. Then we look at all the possible pairs. So if we've got n clusters, anyone want to tell me how many pairs we'd need to compare? Sorry? So the question is, if we've got n data points, how many comparisons do we need to make to find the distance between all of the n data points to the other n data points? Yeah, n into n minus 1 over 2. Okay, so this is a lot. This is not going to be very efficient because you've got a big number to compare here, but that's what you'd have to do. You'd have to compare all of those pairs. And then once you've done that, then you merge the ones that you found to be the closest. You merge that pair. And once you've done that, then you've now got k minus 1 clusters. You had 100 clusters, you've merged one, merged a pair, you've now got 99 clusters. Now you go around again and do the whole lot. Now, fortunately, because we've only merged 2 data points, we don't need to calculate all 99 times 98 over 2 distances again, because most of them are not changed. The only ones that are changed are the ones that involve the data points in the ones that we've just merged. So actually, we only need to calculate another 98 measurements, and the rest of them are all going to be the same. So we just need to keep them somewhere. And then we keep going around that loop. And as we go around that loop, the total cluster cost will get bigger, because as we merge things, it's like tension is going to be built into the model that says the clusters are not quite perfect. A perfect cluster is where the centroid is exactly the same as the data points in it. If they're not the same, we've got this cluster cost. And so as you make the clusters bigger and bigger, the cluster cost is going to get bigger. And we can show this on what's called a dendrogram. So here, let's say we've got this picture here of 12 different data points. As we merge these, we start off with them all in their own little tiny clusters. And the total cluster cost at that point is 0. First of all, we're going to merge 2 points that are close to each other. And on this diagram, it looks like 10 and 12 are the closest. Next ones would be 4 and 11 would be the next closest. And as we merge 10 and 12, that's got a cluster cost that takes us up to 0.8. Once 4 and 11 merge, we're now up at 0.9 as the total squared distance. As we go up, we can see more clusters merge, and then finally we get to the top and we've got a whole big cluster with all of them in. But what we often see on these dendrograms is that there's a natural gap. So here we can see a natural gap that occurs once we've merged into 3 clusters. You have to go quite a long way up until you start then merging into 2 clusters and 1 cluster. And so visually, that would suggest that perhaps 3 clusters is a natural clustering to use. And sure enough, if we look visually, you can see that that's reflected in the fact you've got sort of 1 cluster here, 1 cluster here, and 1 cluster there. And so this dendrogram, you can use this to cluster things even if they're in a really high dimension. Here we happen to be able to see it because it's in 2D, so we can visualize it very easily. Imagine if you're in 100 dimensions, you can't do that, but you can still do the dendrogram. So this can be very useful when you're clustering very high dimensional data sets. So this large drop in the dendrogram really suggests that there are natural clusters that are being forced together. So it does give you a nice example, a way of choosing where those clusters are. It is expensive though, because you're having to do the clustering at every level all the way up. So if you've got huge amounts of data, that may not be the thing that you need to do. It doesn't scale very well with large data sets. And so just the final slide on here is just to give really a detailed example of what you would do at the starting point and how you would merge these two. So first of all, at our first step, suppose we had an example with this time 6 data points here, and we would calculate a dissimilarity measure of our n into n minus 1 over 2 dissimilarity measures here. We then, in order to do the first clustering, we need to look over all of these dissimilarity measures and find the smallest. And the smallest one is this one, 3. All the other dissimilarities are larger. So we choose 0.3 and 0.5 and merge them into 1 cluster. Once we've done that, we've now got our merged cluster 3,5 that replaces these two, and we can see that many of the dissimilarities are still the same. The dissimilarity between 1 and 2 is still 4, so we don't have to recalculate that one. But we do have to throw away all the ones to do with 3 and all the ones to do with 5 and recalculate the ones between our merged 3,5 cluster and all the others. And then at that point, we find the next smallest, and the next smallest would be the cluster between 1 and 2, and so on. So we can see here, 3 and 5 merges at this point, 1 and 2 merges at that point, and so on, up we go.
It's not a cumulative cost you're keeping up the y-axis, it's a marginal.
In this case, this is a marginal cost, but you can also express it as a cumulative cost as you go. But for this one, we're measuring the sort of threshold distance where we make the decision on that one. But you can also see a cumulative cost as you go up, and that's the thing that allows you to balance the two. So that's really that for this lecture. What we're going to be going on to in the next lecture is about feature selection and feature extraction. But just in the last couple of minutes that we've got, I'm just going to introduce in outline how the labs work. And these start on Monday, and I'll show you a couple of little bits of introductory information if you've not used MATLAB before. So let's just go on to the projector here. So the lab that we've got is up on SurreyLearn, and the lab runs over 4 weeks. So it'll be Mondays with 2 weeks of labs next Monday and the Monday afterwards, and then 2 more weeks after Easter. And within the lab experiment, there are 4 total experiments. So that's roughly 1 per week. There are combined into one of 2 lab groups. So roughly 2/3 of you are in the morning on Monday, and 1/3 are in the afternoon. In order to balance out the demonstrators, we've got 1 demonstrator in the afternoon, 2 in the morning. So if you're assigned into the morning group, please do go along to the morning group. And don't say, oh, I couldn't get up for the morning group, I'll go along to the afternoon, because we've only got 1 demonstrator, they're going to be a bit overwhelmed. So please go along to the morning group. I know that there are 1 or 2 people that have lecture clashes with both the morning and the afternoon, and so those people can go to part of the morning and part of the afternoon, and that's fine. So many of you will already know MATLAB, which is this is based on. MATLAB, if you've done any programming language, particularly Python or something similar to that, MATLAB is very easy to get into. But in case you have not touched MATLAB before, there is an additional help worksheet which actually comes from the Computer Vision and Pattern Recognition Lab that will introduce you to some of the concepts in MATLAB, like variables and functions that you might want to use. So if you've done any other programming language, MATLAB is sort of similar. It's just it handles matrices and vectors very conveniently. And so that if you were comparing it with, say, C, you don't have to write for loops or double for loops to get matrix operations to work. You just write stuff, and it does matrix multiplication and so on for you. So have a look at the worksheet there. So in terms of little bits of help, there are some useful MATLAB commands that do a lot of the work for you. So there are commands to generate random numbers, build Gaussian classifiers, build a k-nearest neighbor classifier, and so on. So you don't have to write many of those things. Just look at the help files in MATLAB for those, and it will help you to do those. The report is a single document to do at the end. So all of the 4 experiments go into 1 document, should be about 8 to 10 pages. This is not a huge essay that we're looking for you to write. But do include your MATLAB code at the end outside of that. And please write your own MATLAB code, because this will go through Turnitin. And so if you end up with somebody else's MATLAB code, Turnitin will complain. And it just creates more work for everybody. So please just write your own code and write your own words. It saves me having to set up strange meetings with people that I don't want to meet. Okay. The marking scheme, there are things here about each lab has a certain percentage for each thing. So describe the experiment, what you're trying to do. What's the theory say should happen? Tell me. Give the results. Put plots on. Label your plot axes with numbers and what it is that's being plotted. I saw a number last year that just said, 0 to 3 at the bottom and 6 to 5 on the side. What's that? Tell me what those things are. Analysis of the results. What does that mean? What have you just seen? And the MATLAB code there. So put some comments or something in your code so that it can understand what you did, and that will help. Each of the experiments is worth a quarter. So just running through the experiments and what they're involved in. The first experiment, this is about investigating training a Gaussian classifier using the same numbers that you did in your assignment. And so this is the real-life version of the theoretical version that we've just done. So this should help you to confirm that what happened in the theoretical assignment, actually things like that happen in real life. And what we'll try is, in the first part of the experiment, we'll try different sizes of the design set or the training set. How good are those? And so we'll actually find out how good those things are. And just as a hint here, you should find out very small training sets are not very good. The bigger your training set, the better it's going to be. Sort of might sound obvious, but you'll be able to see that in a bit more accuracy there. So that's the first part of experiment 1. The second part of experiment 1 is to do the same thing using the k-nearest neighbor classifier. And so you get a chance to try out different values of k and to compare the results of your k-nearest neighbor classifier with the Gaussian classifier that you built earlier on. And so that will really give a chance to really summarize all of the most of the lectures that we've done so far. So for most people, you'll stop that one at the end of the first week. But if you want to go on to experiment 2, this one is about checking the test set reliability. So with experiment 2, this time we choose different sizes of test set and see how accurate is the test set as an estimator of the error. And in particular, what we want to look at is what's the expected value and the variance of different test sets. So if we try small test sets, how much do the answers differ from each other when we do that? And then this final set is actually a realistic example to say, suppose you've got 100 data points, what's the best way of distributing them between the test set and the training set so that we both end up with a good classifier and know how well it's done? And that's not so straightforward. And so we're going to try out some numbers there to see how that works. So that's the second week. And I can tell you some more about the other experiments later. But things like how much the dimensionality changes and how much things like class separability and error probability work in here. So that's really your experiment. So I won't be there on Monday. So the demonstrators there, and Armin Mustafa, who's some of you may have met, who's doing the tutorials for the fundamentals of signal processing, are running the lab. I'm on the end of a phone if anyone sort of is stuck for things. But these are things where you can start working outside the lab if you want to. So you can start doing these ahead of time. The labs are there to have the demonstrator support to help you to complete the labs. Okay. Yes. Question.
The assessment is based on the final report.
The assessment is
not individually assessed in terms of performance in the lab.
That's correct. Yeah, the assessment is just based on the final report. So actually, if you're fine with all of this and you're very happy to do it on your own, that's fine. Just do it, submit the lab report, and that's it. The labs are set up so that you can get help from the demonstrator to say, what does this question mean? Why doesn't this MATLAB run? That sort of thing.
And the code component, would you normally want that in a separate file or pasted?
Pasted in the end in an appendix. Yes, please. Yeah. Okay. All right. Yes. Question.
There should be 4 small experiment reports and stick in one PDF.
So one report, one Word document or PDF with just one experiment after the other. Yeah, and you could put the MATLAB code either all the way at the end or after each one as you wish. Yeah. All right, thank you very much. Good luck with the lab and see you next Thursday for the next lecture.